We begin our tour through the world of chemical reactions with a look at combination reactions. Okay, so when you're trying to do the classification of reactions and you're looking for a clue as to whether a reaction is going to be a combination reaction, the clue you should look for is two molecules of starting material becoming one molecule of product. So the example of a combination reaction from the previous lesson was solid sodium oxide reacting with carbon dioxide gas to give solid sodium carbonate. So what I want to do in this lesson is look at some additional examples of combination reactions. And the first one we're going to look at is what happens when sulfur burns in the presence of oxygen. And in that case, you get sulfur dioxide gas. And this is a very simple reaction. It is just between elements. And we don't have to do anything to balance the chemical equation. S plus O2 gives SO2. For our next example, we can take a metal, magnesium, and also burn it. So what that means is we have oxygen present, and this is now going to give magnesium oxide. Okay, so because oxygen is a diatomic molecule, we need two magnesiums in order to give us two molecules of magnesium oxide. Third example is kind of neat. Aluminum metal reacts with liquid bromine to give solid aluminum tribromide. I really like this next example. Okay, so ammonia, when it is a pure substance, is a gas. So you can see there's a bottle here called ammonium hydroxide. That is actually what is written on bottles of a solution of ammonia in water. Similarly, there's also a bottle there of hydrochloric acid, which is a solution of HCl, of gaseous HCl. Pure HCl is a gas. So hydrochloric acid is a solution of HCl in water. So both of these chemicals are solutions of gases in water. Well, we've already talked about the fact that gases can bubble out of solution. So when you open a bottle of ammonia, some of the ammonia gas escapes. When you open a bottle of HCl, some of the HCl gas escapes. That's why both of these chemicals are rather pungent and are irritating to the nose because you're actually breathing some of the gas molecules. Well, if these two bottles are opened right next to each other, you can actually get a gas phase reaction between the ammonia and the hydrogen chloride to give ammonium chloride, NH4Cl, which is a solid. Now, initially, if you made enough of this solid, it would fall down and, start to coat the bottles with some white powder. But here you just see this really, really, really fine, small particles of powder forming in the gases. And that's a really neat effect. And this really does work. I've done this myself in the lab. Okay, and then I want to give you an example of an organic reaction. I know that general chemistry courses sometimes shy away from organic molecules. I actually think that's a mistake because organic molecules are just as important as inorganic molecules. And sometimes the example of an organic molecule is really illustrative. Okay, so the organic example of a combination reaction is C2H2 combining with HCl to give C2H3Cl. Okay, all of the atoms that are in each starting material are combined and we have the same atoms in the product. Okay, so why is this an important reaction? Well, we've already met HCl, that's hydrochloric acid. What is C2H2? Well, that's better known as acetylene, which you've probably at least seen at some point in your life. Acetylene is used for torches. If you combine acetylene and oxygen, you get a really, really hot flame that can be used for welding things. Okay, so if you take acetylene and react it with hydrochloric acid, the molecule you get is also known as vinyl chloride. Now, you may not have heard of vinyl chloride, but you have probably heard of polyvinyl chloride. So if you subject vinyl chloride to a polymerization process involving what are known as free radicals, you then get PVC. And of course, PVC pipe is used in most modern plumbing fixtures. Now, since this was an organic example, I just wanted to give you one other tidbit. Organic chemists usually refer to combination reactions as addition reactions. You will study lots and lots of addition reactions when you go on and study organic chemistry, but this gives you a way to make the connection between what you'll study in that course and the classification scheme that you're learning in this course. Okay, so one more really important application of combination reactions is the concept of hydrated salts. Okay, so depicted here on the slide is a bag of Epsom salt that we bought at a local supermarket here. And Epsom salt is magnesium sulfate, and you can very clearly see on this picture the molecular formula. It says MgSO4 7H2O. Now, if I were designing the bag, I would put a lowercase g for the magnesium, but we'll give them the benefit of the doubt. Okay, so what does the 7H2O mean? So if I take a little bit of this Epsom salt and pour it out onto a piece of paper, I just used yellow paper so that you can see the white salt against the yellow paper. Epsom salt is clearly a free-flowing, dry, crystalline solid, just like table salt. It doesn't look like it's got any water. Where's the water? Well, certain salts react with water, and they'll either react with liquid water or water vapor in a combination reaction. Okay, so the combination reaction taking place here is solid magnesium sulfate, and if it has no water on it, we call it anhydrous magnesium sulfate. And it actually reacts with 7 molecules of water to give magnesium sulfate heptahydrate, is what we call it. Hepta is the prefix for 7. Okay, so then how does this work on a molecular level? Well, most of the water molecules actually bind to the magnesium metal, and all of them are incorporated into the crystal lattice. That's why the salt contains water but does not appear wet. Okay, so I want to show you a picture of this crystal structure of magnesium sulfate heptahydrate. Okay, so in this structure, magnesium is green, oxygen is red, sulfur is yellow, and hydrogen is gray. Okay, so focus on one of those green balls. Those are magnesium 2+ ions. And notice that each magnesium 2+ ion is surrounded by 6 red balls, 6 oxygen atoms. And if you look at those red balls a little more closely, you will see that those are actually water molecules. Okay, so there are 6 water molecules bound to each magnesium, and then you can kind of see one more water molecule in the crystal lattice that is not actually bound to magnesium. That's how we get to 7 waters. That just kind of fills up the space between the cations and the anions. Okay, so without the water, all that's in the crystal is magnesiums and sulfates. When you add the waters actually bind to the magnesium. Okay, and this concept of hydrated salts is a lot more general than just Epsom salt. So on this table are an example of some other common hydrated salts. So calcium sulfate is used in plaster and drywall. It's gypsum. It exists as a dihydrate. Copper sulfate exists as a pentahydrate. And this is a really cool one if we look at a picture of it, because when the waters are bound, the pentahydrate is actually a beautiful blue color, whereas anhydrous copper sulfate is just white. A couple of other examples involve aluminum, sodium carbonate, washing soda, also borax, that's another example. And since these anhydrous salts absorb water from the air, we actually say that they are hygroscopic. Okay, hygroscopic is the chemical term for absorbing water from the air. And then another use for some of these anhydrous salts is actually as a desiccant. So if you need a working environment in the chemistry lab or an environment for storing chemicals that is completely dry, that's completely free from water, you actually put in some crystals of calcium sulfate into your glassware, and that calcium sulfate will absorb any water out of the air. And as a result, since calcium sulfate is used for this purpose, it is also known as tryrite. Okay, so that's combination reactions for you. And then in the next lesson, we will move on and talk about decomposition reactions.